What just happened? Sorry, wait. Okay. Okay. Hello, hello, hello. I don't know if you can hear me, but hello, hello. Hello, Fahima. Hello, Yulia. Oh, more people. Hi, Ray. Okay, I'm gonna go. Wait, okay, I'm gonna do this right. Hold on. Here we go. Here we go. Hello, Fahima. Hello. Hi. What? No more people. Well, sorry. Hang on. Okay. Okay. Hello, Fahima. Hello, Yulia. Hi, Rachel. Hello, Grisella. Hello, Anna. Hello, Almadina. Hello, Kareem. Hello, Diana. Oh, sorry. Hello, Shasha. Hello, Kwan. Hi, Noreen. 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 Hello, Marlon. And now a special hello to video. Hello, Kwan. Hello. Oh, Kwan's the only video. Okay. And hello, Kareem, and hello, Yulia, and hello, Marlon, and hello, Grisella, and hello, Rachel, and hello, Anna, and hello, Shasha, and hello, Noreen. Oh, and here's going to be the correct pronunciation of, oh, yes. It's such a relief. Oh, and there's people in the waiting room. But okay, that just totally changed my day. Thank you. Okay. I mean, Noreen. Okay. Okay. And there's more people coming in. Okay. 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 And hello, Kazi. So sorry about that. Totally my bad. Hello. Yes. Hello. Long time no see. Right. Okay. Okay. No. I mean, I sent out the thing late today. It's all very confusing. But good afternoon, Hannah. Wait. We've been through this before. We've been through this before. I even remember the exchange. So it is Hannah, right? Wait. Why am I suddenly? I get one name right. Oh, no, and you're very kind, Kazi. No, I insist it's my fault, but okay, wait, more people are coming. Okay, we're going to start in a second. I know, so it's going to be a short class today. Okay. So yes, no, but most of you did. Thank you all for your responding. I haven't given you the points yet because I got rushed today. And actually, I owe you so much. And I did promise I was going to finish those things this weekend, and I didn't for a lot of you. Someone asked me last week, totally reasonably, when are you going to do those homeworks? And I said this weekend, I totally didn't. I did for some of you, but I did not for a lot of you. And I hang my head in shame. The only good news, consoling news I can say is I will catch up, and we're not like having an exam any minute or anything like that. And it all will certainly you'll get it all back before we have to worry about an exam or anything. But I have nothing honorable to say in my defense. But why am I even talking about that? Oh, because as far funny you should mention that. I think hopefully right now I think this group is on the road for a bunch of A's anyway. But yeah, I can't quite promise the A's for exactly that reason. But I think you're going to get A's if you keep going the way you're going anyway. And I don't know if you know quite how funny it is that Yulia just said that. I have another funny thing about that. But before I forget, yes, right. Thank you, those of you who did notice that I sent the thing today saying that again today is one of those shorter classes. Thank you for responding. You will get the points. But to confirm also, like just like last time, there will be a YouTube that's posted that you watch to compensate for the 75 minutes, but it's not up yet. And it'll be hopefully very clear once it goes up. It'll say like this is to compensate for the time. So any other YouTubes that go up in the meantime, don't or any past, you're welcome to watch anything, of course, please do. But you don't have to worry about it until you actually see it get posted. The thing that will be for the last 75 minutes. And then the funny thing about, I don't know if you know, and I don't even know if I should say this here in sort of public, but I don't know if you know, I don't even know if Yulia knows the joke that she just made, but about that, like, you should all get A's for everyone, because I haven't turned back the homework yet. Well, should I say this? So a funny thing happened to the YouTube channel. Some of you might have noticed, partly or largely, or perhaps entirely, because somebody from another class posted something on TikTok that said something that I hadn't actually, well, see, I'm worried about. Let me just put, whether or not I said a thing, someone, yes, okay, so you know what I'm talking about, right? Maybe I should just let it go at that. Yeah, right. So as it turns out, a lot of people are watching this video right now, or have been. Should I just leave it at that? I'll leave it at that. Tell me in the chat if you want me to explain this any further. But well, here's the deal. It's not true that I said that. I couldn't say a thing like that. I certainly didn't say it seriously. I think they challenged me, like, would you give us all A's if we got you 100,000 subscribers? And at first they said that, it sounded so, I mean, I laughed. I mean, because that's preposterous on so many.
Which video are we subscribing for, Professor? Just let us know. What are we subscribing for? No, I'm going to do that.
For the YouTube channel. No, okay, wait. All right. So I'm going to explain this. All right. Oh, okay. Sorry. Let me back up. Let me explain it. Yeah. All right. So I have a YouTube channel, right? Like all the YouTubes for this class, the YouTubes that I do ask you to watch, do go. I mean, the videos that I ask you to watch go on my YouTube channel. And it is true, like, in all seriousness, that, certainly you do get, like, game participation points if you show that you are actually using the YouTube channel for the academic purpose of being in this class, right? And one way to show that you're using that you're watching the videos, right? I think that you're supposed to watch. One way to show that is to show that you subscribed. And it is true that in this class for you guys, there's a portal. You may have noticed, some of you have used it, like one of the game portals, where it says, like, you subscribe. And if you just show me that you subscribed, not to any particular video, but to the channel, if you just, like, hit I subscribe, which then means you get the notifications and you know exactly when the video comes out that you need to watch. So I do give you points if you subscribe. That's not the only way to get the points. You could also just show me that you watched the video that you were supposed to watch. Like, I'm not making anybody subscribe, but I am encouraging you as students to use the YouTube resource, because it is a resource for the class. But now, if you're confused what I'm talking about, what happened was, in one of the other classes, someone said, will you give us all A's if we get you 100,000 if you get 100,000 subscribers to your YouTube channel in general? And I laughed, because that's preposterous, right? I mean, first of all, it's preposterous. I can't make a deal where I give you all A's, like, for anything, even for, like, not turning back a homework or something. I can say over and over again, which I am saying, that I do think you can all get A's. I can create situations where I'm trying to help you all get A's. I have had situations where the whole class has gotten A's because right? So, okay, all right. So but I can't, like, literally come out and say, like, I'll give you all A's if you all give me $1 million. Like, that's, you can't do that. And I wouldn't do that. And if someone in this group all of a sudden stopped and said, if I made sure you got the Nobel Prize, or if I gave you $100 million, would you give us all A's? My first reaction would be to laugh, because it's so silly even to think that you could give me $100 million, right? Like, or a Nobel Prize. Like, you can't even arrange that anyway. So of course I would just laugh, like, and I might even, I mean, this comes, oh, actually I have a story. Okay, I'll even tell you a relevant story about physics that this just reminded me. Well, like my son the other day, actually, he was asking me, my 7-year-old son, my younger son that you might have met before, he was asking me about the speed of light, which we're going to get to in this class. He was asking me about the speed of light, and he started saying, and he was sort of intrigued that he was saying, is this faster than the speed of light? And I was like, no, that's not. He's like, do rocket ships go faster than the speed of light? And I said, no, they don't. Well, no, first he asked me, do things go faster than the speed of sound? Which, again, is where actually this course is going to. This is actually relevant, so I'm segueing here. We are going to talk a lot about sound and other kind of waves, and then eventually a wave called light, which is even more exotic and strange and interesting. But we're going to talk about sound. And my son was asking, my 7-year-old was asking about sound. And he said, like, can anything go faster than the speed of sound? And I said, yes, totally. Like airplanes go faster, like not all airplanes, but there are airplanes that go faster than the speed of sound. And many of them are used for military purposes, but there are, in fact, commercial jets called like the Concorde that maybe some of you in the class has even been on. I've never been on one, but there are people, normal people, who have been on airplanes that literally go faster than the speed of sound. In fact, the truth of the matter is there are even cars. The sound speed barrier has even been broken on land by vehicles designed for that preposterous purpose, not vehicles that like a normal person could, like other than like Elon Musk or something, could buy. But the fact is objects can go fast in the speed of sound, and all kinds of fascinating things occur when we go fast in the speed of sound. We'll talk about them in this class. A sonic boom certainly is one example of an interesting thing that happens when we go fast in the speed of sound, but other interesting things happen. So it's like completely possible. And the speed of sound is like 300. The speed of sound relative to air at standard temperature and pressure is approximately 340 meters per second, which is more than like 800 miles an hour. It's a little less, it's less than 1,000 miles an hour. It's fast. It's certainly fast, but it's not preposterously fast. And rocket ships certainly go faster than the speed of sound. Rocket ships, in order to escape, in order to achieve escape velocity, which is sort of a tricky concept, but rocket ships, in order to go to the moon, have to go speeds of approximately 40, they have to blast off with speeds of approximately 45,000 miles per hour. Now that's very fast. That's a lot faster than the speed of sound, a lot faster than the speed of sound, but it's not faster than the speed of light, which was my son's next set of questions. He was asking, like, can a cheetah go faster than the speed of light? No. Can a rocket ship go faster than the speed of light? No. So he's asking all these things. And then to bring this back, which is interesting, that it's not so easy to name something that goes faster than the speed of light. And we will get into that. But so then my son said, will you give me $1 million if I come up with something that goes faster than the speed of light? Right. I mean, like we were in a car at like 10 o'clock at night when he says this to me. And I was so proud of him for even probing this scientific idea. I was so sort of psyched. So he goes, will you give me $1 million if I come up with something that goes faster than the speed of light? So I laughed. And then I said, and he's like, no, but really, would you give me $1 million if I came up with, how did he put it? I think he said, if I came up with something that went faster than the speed of light. So I laughed again. He's like, no, but really, would you? And so I said, yes, dude, if you come up with something that goes faster than the speed of light, I'll give you $1 million. Now, I shouldn't have said it. What I kind of meant, and I said, look, dude, if you come up with something that goes faster than the speed of light, first of all, you're going to get the Nobel Prize. You're not even going to need, but like, you're going to be set for the rest of your life anyway. The New York Times is going to be all over you. Like, a lot of people will be giving you a lot of things. And I don't even think you'll be bothering me for $1 million, but sure. Like, if that's motivation, you go. And if you can come up with something that goes faster than the speed of light, I will stand in line to get you that $1 million that I totally do not have at all, and therefore should not even be agreeing to this. But what I'm thinking is, like, I can agree to this because you can't come up with something that goes faster than the speed of light. But I was thinking that he meant come up with, like, make, or like do, or like invent. But what he meant was, can he come up with a concept that goes faster than the speed of light? So 2 minutes later, he goes, did you say that light is so fast that it would travel the entire, like, so he didn't put it in these fancy words, but he said, didn't you tell me once that, right? Yeah, no, seriously. Well, yes, the car ride, I think we're both never going to forget this car ride because, and it does relate back to what I'm trying to explain about the YouTube thing, I promise. And I'm like all over the place here, I'm sorry, but this is all about physics. My son says to me, didn't you once tell me that light could go the equivalent of the entire circumference of Earth 8 times in 1 second? And I was really pleased that he did remember that I had once told him that. And that's true. Let me make that clear to all of you because you're physics students. I'm not saying that light goes I'm not saying light travels around a circumference. I mean, light tends to travel in straight lines. But I'm saying if you took the entire circumference of the Earth and you unwrapped it, right? You took the equivalent, like a circumference is a distance, right? It's 24,000 miles around the Earth. Well, if you just like picture 24,000 miles being stretched out in a straight line, light, the speed of light is so high that light would cover 8 of those, just shy of 8 of those in 1 second. Like, just to put perspective on things, light does travel so fast that it travels the equivalent of 8 Earth circumferences in 1 second. I mean, that's really fast, right? In other words, light has no problem getting from one point on the Earth to another point, any other point on Earth that you can imagine. Light is going to get there in less than a 16th of a second. Any point on Earth that you can imagine, right? Like, light is going to get there in less than a 16th of it. Why am I saying a 16th? Because, you know, light could go around the whole thing 8 times. So it can go around the whole thing 8 times in 1 second. So anywhere you are on Earth, like the farthest anything else could be away is half a circumference, right? Because if it were more than a circumference, you would just like go back the other way, if you understand what I'm saying. But anyway, that means pick any 2 points on Earth that you like at all and try to send a beam of light from one to the other, or anything that travels at the speed of light, such as an electronic message. You pick any 2 points on Earth and send something at the speed of light from one point to the other. It's definitely taking less than a 16th of a second. I mean, that is no wonder we all think of it as instantaneous. No wonder that not just we as people, but no wonder the thinkers, writers, observers, scientists, whether they're philosophers, whatever they called themselves, scholars, for centuries and centuries and centuries, all believe that light travels at infinite speed. They all believe, just like a child believes that light just gets there in no time, because it's not an idiotic thing to believe at all. All our sensory evidence on Earth strongly gives us the impression that light just gets from one place to another in no time, because it does get there in such a small amount of time, less than a 16th of a second, that it takes incredibly precise time measuring instruments even to detect or pick up on the interval of time that it takes. There's nothing that our body can notice. Anyway, so light is that fast that it gets from any one point on the Earth to another in less than 16th of a second. And my son had apparently remembered that I had once said that. So he said, hopefully this is all worth it just for physics to you. So my son said, okay, Dad, you said light could like go around the entire Earth 8 times in 1 second, right? And I said, okay, yeah, right, that's right. And he goes, okay, so if anything were to travel across the galaxy 8 times in 1 second, that would definitely be faster, right? Because the galaxy is bigger than the Earth. And I was like, wait, what? And he goes, well, anything that would go across a galaxy, or anything that could go across 8 galaxies in 1 second would be faster than light, right? Because light travels 8 Earths in 1 second. So anything that would travel 8 galaxies in 1 second would definitely be faster than light, because the galaxy is definitely bigger than Earth. He said that. And I was like, yeah, that's true. And he goes, so I just came up with something that goes faster than light. Anything that goes across 8 galaxies in 1 second. And I was like, I almost drove the car into a tree. I mean, like, obviously that was not what I was like thinking that our arrangement meant when he said it. And obviously he didn't just make a machine or something, but it was pretty freaking good for a 7-year-old, right? Like, he totally did come up with something that went faster than the speed of light. Like, and what he really did was come up with a fantastic visualization. Like, he showed that he had total perspective on what would be required for. So, I mean, do I really think that I owe him $1 million? Maybe not. Like, well, it doesn't matter because I don't have $1 million anyway. But it definitely I mean, he was laughing hard, and I was like, I didn't know whether to laugh or cry. And for the rest of the ride, of course, he was like, "You owe me $1 million. You owe me $1 million." And I was like, okay, the thing is, I don't actually have $1 million. And he literally put me on a payment plan. He's like, here's what we're gonna do. Every time you get a paycheck from here on in, you're gonna give whatever you need to Mom so that we have food. And then the rest you're gonna give to me. And you're gonna keep doing that until you pay me $1 million. He literally put me on a payment plan. Like, right, I know. So, okay. I thought that was actually very clever. I'm very impressed. That's a story about my son, whatever. It does put perspective on the speed of light. Everything I just said about the speed of light is true. We're going to get back to it in the course. But what it has to do with this ridiculous story is, yes, plus interest, right? Oh my God, exactly. Wait, I'm looking in the chat. Right, okay. Yeah, Well, I don't know if he literally said the word payment plan. I think he did actually, but all right. That was it was, and he kept saying, "Are you mad? Are you mad? Are you mad?" I'm like, dude, if you were anybody but my son, I would be very mad and I'd be very scared. But I'm actually so psyched that you're my son. Like, what am I supposed to say? Like, this is awesome. I think I'll tell the whole. In fact, I told him I would tell the whole class. So now I've done that. What it has to do with is in the other class. I think this is this whole class today. I can't even believe we're recording this. You're going to see what a joke this is that we're actually recording this now. Because in the other class, what happened was someone said, all right, listen, if we get you 100, if we, will you give us all, they said, or because I was mentioning something about the YouTube channel and how you get points if you subscribe, but that's not the only way to get the points. As long as you just, like, that's just one obvious way to show that you're using it. You could also just watch a video. I'm not forcing anybody to subscribe. Like, that would be ridiculous. Why would I do that? And I'm not bribing anybody to subscribe. Why would I do that? And then the person in the other class goes, you're not bribing anybody to subscribe? Like, if we get you, wouldn't you give us all A's if we got you 100,000 subscribers to your channel? Like, for it. And so I laughed because I'm like, that's ridiculous. Like, first of all, that's ridiculous. And second of all, that's ridiculous. You're not getting me 100, like, I'm not getting 100,000 subscribers to my channel. That's preposterous. And they're like, no, but seriously, would you give us all A's if we got you 100K? And I'm like, is that a dare? Is that a challenge? They're like, consider it a dare or something. And they were like, it's on. We get you 100,000 subscribers, you're giving us all A's. And I was like, I don't know about this. But I just sort of kept laughing, and I hadn't had the story with my son at that point. So I didn't know how dangerous these situations are. So short story long, as you might have noticed, like 2 days later, one person in the class who has a TikTok and who like is good at TikTok, I guess, she posted a TikTok that said, we'll all get A's if we get this man 100,000 subscribers. Let's go, or something like that. And I forget exactly, but something like that. And like, all I can say is right now I have 10.3K subscribers thanks to that. I mean, obviously most people are not actually, but a bunch of people have started watching and I'm like sending the comments back because, so anyway, this is all like triply embarrassing because I don't even know who I'm talking to at this point. So now I'm wasting everybody's time, not just your time, but other people's time, because we're not talking about anything. And people keep asking me in the thing, are you actually going to give them all A's? And my answer is always the same. They're going to get A's. Like, what's going to happen is they are going to get A's, but they're going to get A's because they're those kind of people. And only those kind of people would know how to do physics and figure out TikTok to that extent and blah, blah. They're going to get A's, but it's not going to be a gift from me. They're going to get A's, and they're going to make sure that there's never any doubt as to whether they got A's because of this crazy arrangement or because they're crazy cool people. They're going to get their A's. And apparently I'm going to get a lot of subscribers, but it's not a quid pro quo. And same thing with you guys is what it comes down to. Okay, wait. Right. Challenge. Well, I don't know if anyway, you guys understand TikTok better than I. Actually, what I'm here to teach today, to tell you the truth, or what we have to start, we actually do have to learn about TikTok in the real sense, like TikTok clocks, like as in harmonic oscillation. But yeah, I don't get it. All I know is, unfortunately now, every time I embarrass myself in front of you people, I'm apparently embarrassing myself in front of other people as well. Right, okay. Right, okay. But yes, thanks to but yes, just for the record too, yes, challenge accept. They are gonna get A's, and yes, okay, anyway. Okay, this is what we have to deal with today. I should totally not post this class. You did motion 3 yesterday, correct?
No, motion 4.
We were trying to do motion 4 yesterday, yeah. Because the Logger Pro did not work for everybody.
Oh, okay.
So some of us did it, some of us didn't, but just because we were having issues, Professor Wohler said that we don't do the formal report for that one.
Got it. Okay, thank you. Okay. This thing that I just wrote right here on the front page right here, have you seen this before in motion? Have you seen this in any motion with Professor Walters yet?
No.
No.
I haven't.
Okay, good. Okay, so it's new. Okay. Wait, let's look in the chat. Okay.
But I think I've seen something similar in the homework.
Yes.
The homework, something similar to that. Yeah.
Yeah, for the homework for me, you're saying.
Yeah.
Yeah, yes, right, good. Yes, that's right. That's what I want to get. I just wanted to see if it was up in the lab yet or not. But right, okay, cool, exactly. Okay. Okay. Okay, and it's been a week since we had class, and I know lab is pressing along, and we see it sort of feels like we've been stuck on going over homework 1 for a long time. I recognize that often happens in this class. It often, the beginning, it often feels this way, and then things seem like just a bunch of pieces are being put down for a while, and then there's this point. Professor Walters may have mentioned this. There's usually this point in this class where all of a sudden a bunch of pieces from lecture coalesce together and all match up with the lab, and things fall into place. It doesn't usually happen right at the beginning for everybody. It usually happens around motion 4 or 5 or something like that. Hopefully it's going to happen soon. In order for that to happen, I have to finally finish anything I was saying about homework 1, which I know has not happened yet. So I'm reminding you, going back to a week ago, we had a mass on a spring. It was going, and again, I know this relates to what you were doing in lab number 1, indirectly relates to what you're doing in lab number 2, motion number 2. I know you've sort of moved, it seems that you've moved past that at this point, but let me still excavate or extract like the findings from this that ultimately will help you in the motions that you're doing right now. So we had a mass on a spring going back and forth, we had a mass on a spring. We initially held it at some position that was displaced from equilibrium, like we held it at rest somewhere other than equilibrium, and then we let it go and it started moving toward equilibrium, and we figured out how hard it was being pulled, at what rate it was accelerating toward equilibrium. It started moving toward equilibrium, and then it got to equilibrium, and we realized, well, it's been building up speed and building up speed, and now that it gets to equilibrium, it still has speed and has kinetic energy, so it keeps on going and starts losing its speed until it gets to a point all the way on the other side where it runs out of all of its speed, runs out of all of its kinetic energy. All of its kinetic energy gets converted back to potential energy. The potential energy must be the same amount as it ever had at the beginning of this entire process. So it gets to a same point of 15 centimeters on the other side of equilibrium. And now it's at rest temporarily, instantaneously there at that position. It has all this potential energy and this force pulling on it from the Hooke's law spring. So it starts being pulled back the other way toward equilibrium. And the whole process repeats again, and it keeps doing this and keeps doing this symmetrically and iteratively and identically, like as far as we could tell, forever, as long as energy is in fact conserved, and as long as there's no non-conservative forces such as friction doing any work on it, right? Like that's what we said. So this thing goes back and forth and back and forth, and we studied versions of it in lab 1, possibly vertical, possibly simulated. But this process of going back and forth is called oscillation, right? And so we answered all these different questions about the oscillation on homework 1, but then the very final question seems to be the most sort of reasonable, fair, seems to be a super fair, sorry. You see the question? Yeah, what did I say? Oh, I'm sorry. Yeah. No, you're absolutely right. No, yes. I didn't mean to say 0. I mean, good catch. That's really good. You totally get points for that. I'm sorry. It's supposed to be 1, not 0. You're absolutely right. But that, other than that, that is the question, right? Yeah. Good catch. Yes. Not 0, 1. Yeah. Thank you. Wait, who was that? I'm sorry. Whoever that was totally gets points. Yeah, Shasha. Thank you. Right. So question 9 seems to be this completely reasonable, fair thing of they name a certain time. They name second number 1. I stupidly said second number 0, but Shasha was right. It's second number 1. They name time, second number 1, and they say, okay, at this time, at t equals 1 second, where is the mass? Now, that is a totally reasonable question. In fact, that's ultimately the question that all physics situations should ultimately boil down to. All physics experiments like should and do, all physics investigations ultimately boil down to you name the time, can I name the space? Or you name the space, can I name the time? But everything in physics is where is something going to be when? Or when was something where? All there is stuff in space and time. So it's this very fair question. It's just saying when t equals 1, where would we find the mass? It's very fair, but it's interesting that we're not asking it till the very end of the whole sheet. We're not asking until we've already done all this other work, because even though it's a very simple question to ask, it's actually, in the case of a spring, and I should say it's a question we've asked a million times before in a million other physics contexts, like free fall, everything in physics 101. We were always asking if 3 seconds have elapsed, like how far has an object fallen or something like that. We've asked this question a million times before. At a given point in time, what is the corresponding point in space? But here, for this oscillating system that you've now looked at for at least 2, if not 3 experiments, 3 motions, there's something about this question that is simple to ask, but not quite so easy to answer, right? And that's what I have to like sort of probe today for whatever remaining time. Let me point out that again, and so that's what we're going to talk about, is trying to get an answer to this question, or how we get an answer to this question. Let me also point out that Shasha is absolutely right to correct me that I wrote t equals 0, but I should have said t equals 1. And I don't want to defend myself like it was a mistake, and she's completely right. But I actually do want to mention for a moment why I could be so stupid as to make that mistake. The reason is because actually, whatever methods we use to figure out this question, in the end of the day, it's not really the number 1 or any particular number that's going to make this question challenging or easy. I mean, the more I think about it, she is right. At t equals 0, we knew the answer because it's given in the problem. So it really was stupid for me to write that. But what I'm really trying to say here is what I'm really trying to say right now is written right here. Oops, sorry. I'm saying that the issue of this real question, it's not ultimately a numerical challenge. It's a physics challenge. It is saying for this situation, can we find an expression, an equation, a relation between time and space, such that if you treat time as the input, we could immediately produce position as the output? Can we derive x as a function of t? Can we derive position as a function of time for a situation like this for all time? And that's and that's really the thrust of physics in the end. We sometimes think of physics when we're first doing physics, or maybe we're in high school physics, we often think of physics as as an investigation where we're asked a series of questions, and then as long as someone gives us the correct equations, we plug into the equations and use the equations to get the answers to our questions. In fact, what physics is really about, and particularly investigative physics or experimental physics or research physics, what it's really about is collecting a bunch of data so that we can figure out the equation, so that we can discover or invent or derive a general relationship between two variables. Physics really isn't about plugging into equations. It's really about deriving or setting up or establishing or discovering equations. What are equations? They are relationships between varying quantities. So our job here, sorry. Oh, actually, okay, just to make it as clear as I can what is going on here, because this is like the real business of physics. We're looking for position as a function of time. We have done this before in physics, and in fact, we've used position functions before in physics. We've gotten used to some so much that we might have fallen into the habit of thinking they were the only ones. So if you look up in the right hand side, like in red, I've written counterexample, just to give you an idea of something that is related to this, but wouldn't be the right answer to this. When we look at free fall situations, when we look at situations where we have an acceleration that's constant and is the constant acceleration of 9.8 meters per second squared, right? Then we rely on a position function. We have a position function there. It's x equals 1f at squared plus v naught t. And if a is equal to the value of g, we plug in g for a. And so anytime we're doing a free fall problem, like in physics 101, right? Anytime we're doing a free fall problem, if you want to be able to name the position for some time that I name, you plug into x equals 1f gt squared plus v naught t. That's an example of a position function. The thing is, that's a position function that respects the given that we have a constant acceleration and that that constant is known and happens to be the value of g. Here, we're looking for a position function like that one, something like x equals 1f gt squared plus v naught t, something where you plug in t and you get out x, something that has one independent variable t and one dependent variable x. But that one won't work here because here the very assumption is not constant acceleration. Here we have an acceleration that's changing at every single position x, because we have a force, the Hooke's law force, that's changing at every single position x. So I'm just saying now we're looking for some kind of function like, in other words, when I say that we're looking for an x equals function of t, I mean we're looking for an expression where the only two variables in it are t and x, where t is the independent, where x is the dependent, and anything else we see in the equation is a bunch of constants. They might be letters, they might not be numbers, they might be numbers disguised as letters, such as g or a or v naught or something, but all those other letters must be constants, not variables, if indeed we have found the kind of answer we're looking for. Okay, that's what I mean. Like any other letter must be a constant. And x equals 1f gt squared plus v naught t has the right form. It's an example of the type of thing we're looking for, but it won't work here because it has an a in it. And here, what we know is that a is not constant. So we're looking for a different type of equation here. Okay. Well, how can we do this? Like, what kind of equation is going to describe position as a function of time? Well, oops. Okay. I'm saying we have to develop an equation. We don't have one to use. We have to develop it. And we have, this class ends at 5. This is a 545, right? Okay. We're going to build a conjecture for, we are scientists. We are not just mathematicians, we're scientists. We're going to take the data that we actually collected in a lab, or that we collected in a simulation of a lab, or even we're going to take the data that we can imagine having collected from a lab, as long as we have did enough other related labs to have a pretty good sense of what the data would look like. And we're going to build a conjecture from picturing that data. And that's an okay thing to do. In other words, what I'm saying in sophisticated terms is we're going to do guess and check. And guess and check is not only scientifically valid, it's kind of ultimately the essence of science, as long as your guesses are refined and experience-based and coming from a place of rationality. Guess and check works and is valid as long as there is a check at the end, right? It doesn't matter how you come up with something, as long as once you've come up with it, you have a way of testing whether it's right or wrong. So that's what we're going to do. Sorry. What just happened? Oh, sorry. Okay, I'm reminding you of what the situation is, the whole homework one situation, but I'm trying to put it in experimental terms here, as though you did something similar to it in lab number one. But let's imagine now that we exactly did homework one as a lab. Like, we have this mass, we release it from rest from a stationary position at position X naught, we allow it to move smoothly toward equilibrium. I'll explain what I mean by smoothly in a moment. It moves past equilibrium, it keeps going. It reaches an extreme point on the other side, X naught on the other side, smoothly stops. I'll explain what I mean by that in a minute. Smoothly turns around and continues and keeps doing this forever, right? That's the situation. That's what we're observing. Now, and I'm going to explain the word smoothly in a second, but imagine now we're taking data. Imagine we are taking data. So what does that mean? And we're taking XT data. Right. So and we're treating T as the independent variable. We're treating X as the dependent variable. So what it says here in blue is we measure at steady, it says we measure position. I'm sure you cannot read this, but we measure positions at steady time intervals, right? So meaning as this mass is going back and forth like this, we just make a decision that at every millisecond or every centisecond or every second or whatever we can handle with the size of the situation, with the size of our measuring equipment, we make a decision that at every given time interval of some size, we just ask ourselves, where is the mass? And maybe we do this whole thing with logger pro or something, that has a certain level of precision like that, maybe we make videotapes, whatever, but we ask, where is the mass at every single millisecond? We know it starts off at position 15 centimeters. So then a millisecond later, where is it? Maybe it's at 14 centimeters. Then the next millisecond, maybe it's at 12.5. Who knows? But that's what we find out, right? We just imagine taking steady position measurements at steady time intervals. We're measuring position as it depends on time, right? Just imagine doing that. I'll go back to the word smoothly in a moment. But if we were to do that, we would make a table of values, right? Now, notice, I don't care, even if you were just doing motion 4, totally different lab, I understand, but notice the pattern. Whatever lab you're ever doing in physics, at some level, what you're always doing, well, yes, at every level, what you're always doing is you're setting some variable as the independent one, frequently time, not always time, but usually time. And then you're making some other measurement at equal intervals in that independent variable. So you're always measuring one thing in response to another. And you're always making a table of values from those two, always. So in this case, the two values are T and X, right? And T is at steady intervals. These could be milliseconds, they could be centiseconds, they could be minutes, it doesn't matter. And then we get some values for X. We know the first one is 0.5. And we know the values are going to get smaller and smaller until oh God, I don't know what just happened. Wait, I'm sorry. Hold on. What just happened? Are we still there? Okay. These values would go until at some point, the values would reach 0, and they would go and go and go and go until they reached negative 0.5, right? And then they would go and go and go, and they would go back to 0, and then they would go and go and go till they were back to positive 0.15, right? I don't know at what times this was, but there would be a pattern of the time intervals would all be equal, and the X values would fall in this pattern where they're going back and forth between positive 0.15 through 0 to negative 0.15 back and forth, right? I mean, and then we would take all those values and we put them on a scatter plot. This is what we always do in every single experiment. And then we would look at the scatter plot, and from the shape of we would hope to find some sort of trend or some sort of comparatively smooth or simple shape in the scatter plot. And from there, we would try to take our best conjecture or guess or use the computer to come up with some sort of familiar equation or expression or function that best corresponds to the shape that we see on the scatter plot. Now, sometimes that's very hard, and sometimes it's not so hard. In this case here, I think it wouldn't be so hard. I think in this case, if we took this data and put it on a scatter plot for which time, right? Time would be the x-axis because it's the independent variable. X would be the vertical axis because it's the dependent variable. Now, again, I know this is not exactly what you did in motion 4, and it's not even exactly what you ended up measuring in motion 1. But I bet without even having done exactly this, you could make a very, very good conjecture or prediction prediction of what this scatter plot would look like, as long as I remind you of two things. One, I think these positions are going to go back and forth. And remember, x equals 0, like the the equilibrium position means crossing the x-axis, right? The x-axis is equilibrium. Maybe I should have read that. So we know that the mass and the mass starts somewhere here, like at 0.15, and eventually it goes over to the other side of equilibrium at negative 0.15. We know that the mass is going to go back and forth between those two values as time progresses. It's going to go back and forth between those two values. The key thing is we know it's going to do that smoothly, right? Like I circled the word smooth on the other page a couple of times. I don't mean perfectly smoothly. I don't mean perfectly smoothly. Nothing happens perfectly in an experiment, but I mean smoothly as things do happen in nature and in the real world. I'm saying smoothly precisely because this is a real world situation. That is, when this mass goes back and forth, I don't think the graph of it's going to look like a jagged sawtooth. I don't think the mass is going to go from 0.15 to 0 down to negative 0.15, and then in no time whatsoever grind to a complete halt, and then in no time whatsoever instantaneously turn around and start going the other way. In other words, I don't think this is going to act like a cartoon. I think everything this mass does is going to take time. If it's going to stop eventually at negative 0.15 on the other side, it's going to slow down as it's getting to the stopping point. And then if it's going to start speeding up from 0, it's going to speed up smoothly. If acceleration, so if speed is going to change from one number to a negative number, it's going to smoothly pass through 0 in order to do it. If acceleration is going to change from one positive number to a negative number, it's going to smoothly pass through 0 in order to do it. I think everything is going to be smooth, not perfectly smooth, but it's going to be more smooth than not, because this is real life, because it's not a cartoon. And in real life, you can't get from 0 to 2 without passing through 1. And you can't get from -1 to +1 without passing through 0. In fact, you can't get from 0 to 1 without passing through 1/2. Nature cannot bring this mass from any point in space to any other point in space without passing through all the intervening points in space. So whatever shape this graph looks like is going to be smooth. There shouldn't be any corners or skips or jumps in this graph, because jumps and corners only occur in fictitious idealizations like cartoons. In other words, I think it's pretty reasonable to believe, and you could test in lab, that if you took a bunch of data of this mass and threw it on a scatter plot, it seems to me the data would fall into a curve that looks pretty much like this. Up and down smoothly, right? I mean, is that now? What kind of graph? You know that from math. It'll be 15 minutes. And again, like, you could literally do this in the lab, or I think even in your head, you can be pretty confident that the more data you took in lab, the more the graph would look like this. What is that graph called in math? Like, what function is that? I mean, is that is that a parabola? Is that y equals t squared? Is that a tangent graph? Is that a exponential graph? Like, what is that called in math, that graph? Have I lost everybody?
Wait, this is the cosine graph, right?
I totally think so. Yes, I totally agree. Is that okay? I mean, are you saying it in that tone of voice? Because, I mean, are you? Yes, totally. So, and by the way, I totally agree. And that is my point. And thank you, by the way, for saving me, because that was like very awkward and nerve wracking for me. And you get tons of points and all that. But can I ask one question? As long as you have the guts to say this, can I ask one question? And she's right. Again, I'm not trying to trick anybody. It's totally right. That's a cosine graph. In fact, what we're really saying is, I think if we're looking for a function that if we're looking for a function x of t that describes what an oscillator does, I think cosine looks like it's going to be a very good conjecture. I may not have proven it yet, but it looks like a very good way to describe what x is as a function of t. One question, Yulia, how did you know, why did you say, and you, again, it's correct, so this is just a probing thing, how did you know cosine rather than sine?
Because the sine goes the other way around, like upside down. I don't know how to explain it, but
okay.
Where on the where it's gonna cross the x-axis, it would have been on negative 0.15 instead of 0.15.
Oh, in fact, okay. Okay, yes, except I'm going to go even one step further and say what Noreen is saying. Noreen is saying, yeah. So first of all, okay, to everybody back. So Yulia is totally right and totally awesome, and thank you guys for paying attention. That does look like a cosine graph to me. It is a cosine, and cosine is going to be the answer here. And I just want to also, and yes, it looks very similar to sine, but there's something about sine that almost looks like upside down or different from it. And the real specific way to put it is what Noreen said, which is that sine, like if I made this literally upside down, it would be negative cosine, in fact. But if I instead had gone like a different color, if I had gone like this, and I think this is also, I know Yulia knows this would have been sine, right? Exactly. So what Yulia is now saying, and Noreen is saying, is that the fact that this thing didn't start at the origin, that it started somewhere other than the origin, is what suggests that it's cosine, not sine, which I agree. Let me also tell everybody, physically, this makes sense. This is a cosine. And the reason I started, like the reason I drew it that way is, think about it, like in our problem, in the situation, we didn't start the mass from rest at equilibrium, right? Like at t equals 0, the x for this mass was not 0. If it had been 0, the thing would never go anywhere because 0 is equilibrium. We deliberately started the mass somewhere other than equilibrium so that when we let it go, it actually did move to equilibrium. So we literally do start off the origin. We start with a y-intercept of, in this case, 0.15, or what we're calling x naught. And hence, it's a cosine, not a sine, right? I mean, so I'm agreeing. So Noreen, yes, totally, and Yulia, yes, totally, and points for the world. So what this suggests, now we're almost there. I know we only have 10 minutes. What this tells me is that at least it tells me that maybe if I were a mathematician, I would have a hard time coming up with this function. Maybe not. But as a physicist, as someone who's working in the lab or someone who's thinking in terms of data and measurements, I have a good leg up on making a prediction on, I have a good leg up on coming up with the equation that I need for oscillation, because I can picture how the data would fall onto a graph, and the data would fall in the form of a cosine graph. So I think we are going to guess cosine here. What? So remember again, our whole goal here, and I do know that we only have 10 minutes, but our goal in the 10 minutes is to get x as a function of t for all time, for any oscillating system like this, so in other words, again, I don't really care about just only when t equals 1. I'm trying to get for all time a situation whenever from here on in, if you put a mass on a spring, if you put an oscillator in front of me, so really what I'm really talking about is like motion number 1 and motion number 2, and I think even motion number 3, anytime from here on in you put some oscillating back and forth thing in front of me, if I want some rule or some function or some relation between time and space, if I want to be able to predict, if I want an equation of motion, is really what we're saying, or what some people call a position function. If I want to know how position is dependent on time, what I'm conjecturing so far is that cosine is the way to go. Okay, but I'm not done, and it's going to be correct. I'm not like wasting anybody's time on purpose. Cosine does seem to be the shape that that oscillation suggests, but I'm going to write it like this. I'm saying like, oh, yeah, x equals. Oh, very good. Oh, you're a step ahead of me. That's great. Okay, I totally agree with that. And since you're going fast, I'm trying to speed up to catch up with you. But yeah, that's really good. Let me explain why Yulia just said that. Let me start by saying right now I have this conjecture. Just looking at the axis. Well, I mean, just looking at the scatter plot, I'm thinking x is some kind of cosine of t, some kind of cosine. I put blank spaces around the cosine for a specific reason. And one of those blank spaces is going to cover the thing that Yulia just said. I put blank spaces around the cosine because I'm a scientist, because I'm not just a mathematician. And all this is ultimately coming from and relating back to measurements. So everything involves units, right? And time is measured in seconds. That's the input. The ultimate output is going to be measured in meters. You can't take the cosine of a second. You take the cosine of something measured in radians. And when you take the cosine of something measured in radians, what is spit out is something dimensionless, like or you could take the cosine of degrees, but as a physicist, I prefer radians. But when you take the cosine of, for example, pi over 3 radians, or if you like 60 degrees, what you get is 1/2. You don't get 1/2 of a meter or 1/2 of a degree or 1/2 of a kilogram. You get the number 1/2, right? So what I'm saying right away, with 8 minutes left, I'm going to address Yulia's thing and my thing. I'm saying I think x is going to be some kind of cosine function of t, but it can't just be directly x equals cosine t. That would not work because t is measured in seconds and you cannot take the cosine of a second. So something's going to have to be multiplied by the t in order to cancel out those seconds and put in radians. So there's going to have to be some constant multiplied by the t, some constant number measured in radians per second, so that the seconds cancel out with the t. Sorry, and radians are left over, and you take the cosine of radians. Then cosine is going to spit out just a pure number. We're just going to get a pure number, but we want our final answer to be in meters, right? So there's going to have to be something here that is measured in meters, right? There's going to be two constants in our equation that have units in them to make this, if this has any chance of working out at all. It's going to be not just cosine, but a constant of some kind times cosine of some kind of constant multiplied by t. Now let me deal first. I know we have 6 minutes. Let me deal first with what Yulia said in the chat, because she already anticipated one of these constants. What Yulia is saying is, oh, I know what constant better go before the cosine. I'll tell you. She's saying, well, yes, it's going to be some kind of constant in meters for sure. It's going to be a specific displacement or position measured in meters. In fact, she's jumping ahead and wisely, thankfully, saying, you know, it's not just any old meters. It's going to be the initial number of meters that the mass was originally at in the first place. Like Yulia is saying that the thing that better have units of meters is going to be x naught. And she's totally right. If we had more time, I would ask her to explain why she's right, but I'm not going to because we only have 5 minutes. So I'm going to explain why Yulia is right. I know she knows. She's saying there's going to be an x naught there because we know at t equals 0, we know at t equals 0, x is supposed to be x naught, right? In this case, positive 15 excuse me, in this case, 0.15 meters, right? We know what is x naught, what's the initial position? It's wherever the mass is when t equals 0. Physically, we know that that value is called x naught, and in this case happens to be 0.15 meters. Mathematically, what I think Yulia is remembering, and I want to remind you all, mathematically, the cosine of 0 is 1, right? Again, if we had more time, I'd pause and ask you guys that, but I'm just reminding you, the cosine of 0 is 1. So if I plug in 0 for t, then no matter what constant is right next to that t, I'll have something times 0. Anything times 0 is 0. So then I'll take the cosine of 0. That'll spit out a 1. So at t equals 0, I'm just going to have a 1 sitting there. So the constant next to it better be x naught, because x naught times 1 is x naught. And that's what x better be when t equals 0. You see what I'm saying? I'm saying, in other words, we already physically know one value, the extreme value of t equals 0. Let's make sure that the math captures that. If the constant that we put before the x naught is, before the cosine is x naught, then so far everything works out nicely. So I'm agreeing with Yulia that the constant that better go, so the constant that's going to go there is x naught. It fulfills the two conditions. One, it has the right units. Two, it returns the appropriate value for t equaling 0. So the only other question is what constant goes in the other dash. I don't know yet. I mean, I do, but like at this stage, I'm just making up an expression. I don't know anything about that other constant, but it is going to be a constant. So I'll just make up a name for it. Like, I'm not going to call it x. X is already a variable. I'm not going to call it t. We're already using those. I'm not even going to call it y or z or anything, because those are variable names, and that would connote that there's a whole other variable going on here. There isn't. I just want some letter that stands for a number that's never going to change here at all. I could call it whatever I want, but let's call this. So I call whatever I want. I'm going to use the same thing that all other physicists use. It happens to be a Greek letter. You could use anything you want. Okay, and we have 2 minutes. I'm going to go one more page and just explain this omega thing, and then we're done. Okay, I'm not assuming you know anything about omega. I'm just making it up. Oh my God, my son's about to walk in right in the last 3 minutes. I'm saying this is the last page and last thing I'm writing. And we're going to get, and we're about to end, and we're about to be interrupted too, but I'm saying this. Omega, that letter, it looks like a W. It happens to be the lowercase Greek letter omega. We could have used anything. Traditionally, we use an omega there. I'm not assuming that we already know anything about omega. I'm introducing it now. It's just a letter, but what it's going to stand for, oh, sorry, I don't mean angular. I'm sorry. I mean, oops. It's going to stand for angular frequency. That sounds very fancy. That sounds like I'm introducing new information. I'm not. I'm just saying, based on the units that it has to have, and it has to be there because of units, it's measuring some kind of rate, right? Like velocity rate of speed is meters per second. This is some kind of rate in time, but it's not meters per second. It's radians per second. It's measuring a rate. What is it measuring? It's measuring a cycling rate. It's measuring like how many humps in that cosine graph we have per unit time on the x-axis. It's measuring how many times that cosine graph returns back from 0 to 2 pi again. It's measuring how rapidly the oscillation occurs, how rapidly it cycles, only it just happens to measure it in radians. Why? A radian is a measurement of angle. What's an angle? An angle is a portion of a circle, right? oh, sorry, the first word in the last sentence is measured, I think. Hold on. And give me one second. I know we're about to go over, but hello. Okay, I'm just about to, hello. Okay, I just have to finish this. We're over time. Let me just finish this really quick. Okay. Love you.
Hello, class.
Okay, but they're
My
late.
name is Felix.
Yes, but I'm holding them late. They're late. I've got to let them go. I've got to finish now.
And bye.
Okay. Thank you. And I'll be up in 1 second. Okay, love you. Okay. Oh, starts with a C. Oh, cycling. I'm sorry, cycling. Okay, and I'll say this really quickly. I know you all have to go. Thank you. Sorry about that. Yes. What I'm trying to say is that omega measures the rate at which this thing cycles, but it's measuring it in radians, which sounds crazy. Why would it measure in radians? Well, one thing it has to, because cosine can only be taken of a radian, but also because radian is a measurement of angle. Angle is a portion of a circle. Like what's a right angle? It's a fourth of a circle. What's a 180-degree angle? A half of a circle. What's a 360-degree angle? A full circle, regardless of the size of the circle. An angle is always recognizable as a portion of a circle. So we are thinking of each cycle of this thing as like a circle. Omega is the rate at which this thing goes back and forth, but measured in portions of circles. Bottom line, and that's all that's all we know about omega right now. That's all we need to know. It forces the units to work. So our conjecture here is, putting it all together, is this. This does turn out to be the right. And so to get the answer to the last question, I'm sorry, I'm going over and if you have to go, just go. And you'll see it on the recording. But if you have to get the answer to the, oh, thank you very much. Thank you. And I'm just about done. But to get the answer to the very last question on the homework, you just plug in 1 for t and it'll spit out x. But what we'll do next time, and what you're going to do in lab, is actually verify and show why this is necessarily correct. Right now, it's just a conjecture. We have to verify that it's correct, but it is correct. So that is the position function. That is the equation of motion for any oscillating system. That is it. I'm done. Thank you for staying late. I'm sorry. I will turn off the recording. I'll just stay for a second if there's any questions or anything.
Bye, everyone.
Bye. Cool.
Sticky wants to say bye.
Okay. Bye.
Ah.
Okay.